But once the errors are 0, you can't go through 0. All right, the last thing is, what are the most important observations that control the solution? This shows conventional weather observations from radiosondes, which are balloon soundings. And essentially, well, there's a bunch of things on here, including cloud winds and surface observations and whatnot. But the size of the symbol shows you where the measurements are located that have the biggest impact on the forecast. And lo and behold, they are radiosonde observations. They're vertical profiles of the atmosphere right in the vicinity of that trough in the westerly jet stream, that feature that we identified as things being sensitive to. And the last calculation shows if we assimilate one piece of information, and it is the westerly wind at 250 hectopascals. So this is one level from one radiosonde at a location in Mongolia. So we found out that that was the most sensitive location. And then we just assimilate that one wind measurement at that one level near the jet stream, right near the heart of that feature. We get that perturbed initial condition, and then we take it out 48 hours, and we get this really big response, and lo and behold, the signal is large enough right where we predicted it would be, right in the heart of the tropical cyclone. So a localized response, roughly along the lines of what we thought it would be, and it's a deep signal. It goes all the way up to that feature, which was in the jet stream and worked its way across the coast. So I think this is a really cool example of you really can find a needle in the haystack, the one that really matters, and quantify its impact. All right, so the very last thing I'm going to talk to you about is using data assimilation in the time domain. So we're used to thinking about doing data assimilation to produce an initial condition that we then use the forecast model to make the forecast with. This is something we call ensemble forecast adjustment, which uses the observations to correct existing forecasts. So the way to think about this is there is some discrete time interval between data assimilation, right? Producing initial conditions that we run forecast models. At NCEP for the global models, it's 6 hours. For the European Center, it's 12 hours, which means you have to wait 12 hours until you get the next forecast, right? The next forecast cycle. But as soon as, or even before you get access to that forecast, new measurements have been made which inform upon the system that we didn't know about when we first did the data assimilation, right? So the question is, can we use that information to correct the forecast on the fly before we get to the next time when we get a new data assimilation, a new forecast, right? So I think there's gold here. This is how money gets made. There's new information that nobody else knows about or knows how to use, and you can improve the forecast. All right, so yeah, this is just a restatement of what I just went through. People have been thinking about this for a long time. There is a statistical way that people have been doing this in NOAA called LAMPS. And it essentially blends something called model output statistics, which is a post-processing of forecasts with new observations that come in after the forecast model is run. Here we're using data assimilation in the time domain with a similar goal of updating forecasts with new information. And it's essentially using these temporal covariances in the ensemble sensitivity analysis in time, just like we talked about earlier in the lecture. Okay, yeah, so the basic idea is we allow assimilated observations to adjust not only the current analysis, but also the future forecast states. It's a fast forecast update. And again, because we're not basing any simulation of the model off of this, we can update whatever we want. We can just update the surface, or we can update some function of the state. It's completely flexible. Yeah, we can update anything we want. We don't even have to own the model, right? I don't have access to the code for the European Center, but if I have access to their ensemble forecast grids, and an observation stream, I can update their model before they make their next forecast. So yeah. So here's an example that my student Luke envisioned, that some forecaster would have maybe a real-time running display where they have some forecast from the last data assimilation system. This is for the 2-meter air temperature at Dodge City and in the United States. And so basically it gets warm in the afternoon, it cools off at night, gets warm the next afternoon, cools down at night. And in the 6 to 12 hours or so after the forecast was released, but before the next forecast cycle, we've got new observations there. We know whether the forecast is on track or not, and we can use the ensemble information at time to correct the whole forecast. Right? So that's the basic idea, that you'd have some way to, on the fly, continuously update the forecast. So this was originally proposed by Brian Etherton. He called it preemptive ensemble forecasting. He illustrated it in a very simple two-dimensional fluid dynamics context and showed that forecasts of vorticity, which is a measure of spin, can be improved by assimilating observations at some intermediate time. So for this to apply to operational ensembles, what we'd really like to have are large, well-initialized ensembles. The larger, the better. And by well-initialized, we mean an ensemble that is faithful to the measurements in some statistically appropriate sense. And that's not always the case. The linear relationship may quickly decay in the forecast. So we need relatively frequent forecast output. Hourly is perhaps the most valuable. And high spatial resolution as well to map onto the observations. What we have are ensembles that are not necessarily well calibrated for short forecast times. The European Center, I believe they still use singular vectors to populate their ensemble forecast system. These are things that grow very rapidly and will give a lot of spread in the forecast on short lead times. That's not good for what we're trying to do. We need something that has realistic errors consistent with the observations. The ensemble systems tend to be relatively small. Some of them, like European centers, are as large as 50. And the forecast output is not as frequent as we'd like, and the models are too coarse. But the idea is there. And we've tested it. Basically, that's what this slide shows. So we have a bunch of surface pressure measurements and temperature measurements coming from primarily land stations and some ships and buoys. And we're going to see if we can improve the forecast after it was made and before the next one becomes available. Now we're going to do this with two operational ensemble systems. The first one is from the Canadian Meteorological Center. They, at the time, were and still are using a bona fide ensemble Kalman filter for their operational analysis and forecasting. And we also, in the red, are looking at the European Center. And at the time, I don't think they had yet switched to using their hybrid system. But in any case, the first thing you should notice is for the pressure at mean sea level, the mean square error, over this time period from a 12-hour forecast to a 30-hour forecast is increasing with time, so that's error growth. The other thing we notice is that the errors are smaller in the European Center compared to the Canadian Meteorological Center. The dashed line shows us the original forecasts from both of those modeling systems. And then the solid line shows us what happens if we take the pressure measurements at 6 hours and use them to correct the forecast. And lo and behold, when we verify that, we actually do reduce the error in those forecasts. So essentially it works. The ensemble is reasonably well calibrated. This is what happens to the ensemble variance. It drops roughly consistent with the drop in the error in the ensemble mean. For temperature, the lead time over which we can do this is shorter. It's more like about 12 hours or so. And we can't do much beyond that. And more so with the Canadian model than we can with the European Center. So it's proof of concept. It works. We seem to have the ability to improve forecasts before you can get access to another forecast initialized with future observations. And this is a summary map showing you that this does physically sensible things. So this is a map of a forecast over Europe. So here's Spain, France, Scandinavia, the UK. And we're looking at a map of pressure in the contours. And then we have in the greens and lavenders the change in the forecast error at the stations. And then we have in the blue and the reds the change that we got in the forecast from doing this process. So the important thing is you can see that for the most part, when we got to the future, where we corrected those forecasts and we looked at the station data, we see mostly greens here, which means we actually reduced the forecast error. The other thing we see is that for like little features like this low pressure system here off in the Mediterranean to the west of Sicily and Italy, that physically what's happening is the measurements were telling us to shift the low to the west coherently. Right? So there's a very clean, coherent signal here. The measurements knew that the forecast was off. They detected that the low was moving too quickly. They shifted it to the west, and that verified very well with those measurements at the later time. So anyway, once again, the take-home message is it seems to work. And probably will work better as we get better ensemble systems. Okay, so the wrap up here for lecture number 4 is that data assimilation provides us the ability to measure the impact that measurements have on the analysis and the forecast. We can also find the best places for new measurements, that's targeting or optimal sensor placement. We can use these techniques to gain physical insight into the system, and we can improve existing forecasts on the fly, which can be used for fun and profit. All right, that's a wrap. Thanks very much.